Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In the last video, we learned that limits are about approaching, not arriving. We saw that a limit can exist even when a function isn't defined at a point, and that the value of a function doesn't necessarily tell us anything about the limit. Today, we're going to push that idea a little bit further. What happens when a function doesn't just approach a number, but grows without bound? What does it really mean when a graph's shooting upward or dropping off the screen? And how do we describe that behavior precisely using limit notation? We'll use the graph of the first equation to help us build some understanding. But before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. Now consider the graph of f of x is equal to 1 over x plus 1 squared. We have already plotted the graph on the screen. So the denominator here is x plus 1 squared, which means that x cannot be equal to -1. But what we're interested in is the behavior of the graph close to -1. So now because we have a squared on the bottom, we know that this is always going to be positive. So our denominator is always going to be a positive number. And when we're close to -1, x plus 1 is either going to be a very small negative number or a very small positive number. And once you square that, it's always going to be a positive small number, which is why when we do 1 divided by that, it ends up approaching infinity. Hence, the shape of the graph over here. And this dotted line that you see at x is equal to -1 is what we call a vertical asymptote. So now let's take a look at the actual definitions. We're going to let f be a function that is defined on both sides of a number a, except possibly at a itself. Then we say that the limit of our function f of x as x approaches a is equal to infinity if the values of f of x can be made as large as we want by taking x sufficiently close to a, but not equal to a. So that's just a fancy way of saying that as x gets closer and closer to our number a, then our function f of x is approaching infinity. And similarly, we can replace that infinity with negative infinity for large negative values. And now the vertical line, x is equal to a, is what we call a vertical asymptote. And you saw that in the earlier example with that vertical dotted line. So this line, x is equal to a, is called a vertical asymptote if at least one of these following statements is true. So this is really just saying that at least one of these limits is approaching positive or negative infinity. So one of these limits is approaching positive or negative infinity. And now let's go ahead and take a look at an example. So here we have drawn the graph of f of x, and we want to find these limits on the left side. So the first limit is x is approaching 1 from the negative side. So 1 is right over here. And because we're approaching from the left-hand side, we're going to look for the graph to the left of 1. And that is going to be this piece right over here. So if we're approaching 1 from the left side, then we're going to be following this graph. And we can see that as we get close to x is equal to 1 from the left side, our function f of x is approaching 4. So therefore, the first limit is going to be equal to 4. Now the second limit, we're approaching 1, but this time we want to approach it from the right-hand side. So again, we're going to look at our 1, but this time we're going to look to the right of it. So from the right side, we're going to be approaching from this curve. And we can see that as we get closer and closer to x is equal to 1 from the right-hand side, the value of the function is approaching -2. So therefore, the second limit is going to be equal to -2. Now the third part is asking us for the overall limit as x approaches 1. And since the limit from the left side is equal to 4, but the limit from the right side is -2, the overall limit does not exist because we have two different values. The fourth part is not a limit. It's asking us for the actual value of the function at x is equal to 1. And we can see that that is actually equal to 4 because we have a solid dot there. So f of 1 is equal to 4. Our next limit is x approaching 6 from the negative side. So 6 is right over here. And if we're approaching 6 from the left-hand side, we're going to follow this curve, and we can see that our function is approaching a y value of 5. So we would have 5 as our limit. And then if we're approaching from the positive side, so from the right-hand side, we will follow this curve here, and we can see that we are also approaching a value of 5. So the limit of our function f of x as x approaches 6 from the right-hand side is also equal to 5. And since the left side limit is 5 and the right side limit is also 5, that tells us that the overall limit as x approaches 6 for our function f of x is going to be equal to 5. However, notice that the actual value of our function f of 6 is right over here, and that value is 2. So f of 6 is equal to 2. So this is a classic example where the limit is different from the actual value of the function at a particular point. The next limit we want to find is the limit of our function f of x as x approaches 9 from the left-hand side. So if we follow the curve from the left-hand side, we can see that this curve is going towards negative infinity. So the limit of our function f of x as x approaches 9 from the left-hand side is going to be negative infinity. And when we approach 9 from the right-hand side, we can see that if we follow this curve, we're now going up towards positive infinity. So therefore, this limit is going to be positive infinity. And now the limit of our function f of x as x approaches 9 is going to be does not exist. And just a quick note here. Having the limit of a function going to infinity or negative infinity is the same as saying that the limit doesn't exist, because infinity is not an actual number. So some textbooks will use infinity and does not exist interchangeably. And now finally, the last part is we're asked to evaluate the function at 9. But we can see that we have a vertical asymptote at 9, so therefore this would be undefined. And this is because 9 is not within the domain. So notice that we use does not exist for limits, and we use undefined for actually evaluating the function at a particular point. Moving on to the next example, we are asked to find the limits of these functions using our precalculus knowledge. So the first one, we're asked to find the limit of x plus 2 over x minus 1 as x approaches 1 from the right-hand side. Now we can see that our numerator is going to approach 3 as x approaches 1 from the positive side. Our denominator, because we're approaching 1 from the positive side, that tells us it's going to be a number that is bigger than 1. So a number that is bigger than 1 minus 1 is going to result in a positive number. But because we're getting very close to 1, this is going to be a very small positive number. So we have positive 3 divided by a very tiny positive number. So that means this is going to be approaching positive infinity. Our next question is to find the limit of ln of x squared minus 4 as x approaches 2 from the positive side. Now just a quick refresher. The graph of ln of x looks something like this. So if we have x is approaching 2 from the right-hand side, that means our x is going to be a value that is a little bit bigger than 2. And when we square it, that number is going to be a little bit bigger than 4. So therefore, x squared minus 4 is going to be a positive number, but again, it'll be a very small positive number. So we're taking ln of a very small positive number. So looking at the graph here, we can see that that means this is going to be going towards negative infinity. So therefore, the limit here is negative infinity. And now for our last example, we want to sketch a graph of a function that satisfies each of the following conditions. And note that there are many different ways to do this. So the graph that I draw could be very different from the graph that you draw. So we're going to go ahead and draw our x and y axes first. So this is -1, -2, +1, +2. And then we have our y values right over here. All right, so the first one is we want to have the limit of our function f of x as x approaches -1 from the left-hand side to be equal to -2. So that means when x is approaching -1, which is this value here, we want the y value to be approaching -2, which means it's going to be somewhere here. And the easiest way to do that is I'm just going to draw a horizontal line at y is equal to -2. But I don't know what the behavior is at -1 yet, so I'm going to leave it like this for now. Next, we want the limit of our function as x approaches -1 from the positive side to be equal to 3. So that means from the positive side, we want the value of our function to be up here. So therefore, we might want something like this. And now we have f of -1 is equal to 0, which means that the actual y value of our function at x is equal to -1 is going to be 0. So therefore, I'm going to be putting a solid dot right over here. So now that tells me I need a hollow dot here and a hollow dot here. Perfect. So now we have satisfied the first three conditions. Next, we want the limit of our function f of x as x approaches 2 to be equal to 1. So notice how this is just x is approaching 2, which means we want both the left side limit and the right side limit to be approaching 1. So that means we want to be approaching this point right over here. So that means I'm going to be continuing with this line. So let's say it looks something like this. And then just to finish it off, I can say that the other side maybe looks something like this. However, notice how I have now put a hollow dot over there. And the reason is because of our last condition, which says that f of 2 is undefined, which means that x is equal to 2 is not within our domain. And this is why this point is removed from the graph. So this would be a graph of a function that satisfies all of these conditions here. You could draw something that looks completely different, but the important part is that these limits need to be exactly where they are, but the behavior of the graph here, here, and here can be different. And now let's do a quick recap of what we covered in this video. We saw how limits don't always need to approach a finite number. Sometimes they can increase or decrease without bound. And we saw what a vertical asymptote is. It occurs when the function values grow without bound, and we can use either positive or negative infinity with our limit notation to represent these situations. We saw the difference between D and E, which is does not exist, and undefined. So we use does not exist for limits, and we use undefined when we're talking about evaluating a function at a particular point. And finally, we worked with both graphs and algebra and logical reasoning. We used graphs to help us visualize limits, but algebra and logical reasoning allow us to predict behavior without actually graphing them. And now it is your turn to give this a try. Without graphing this function f of x here, can you determine the following limits? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on limits in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.